A time series is a set of observations over time, and the Tutoring Center has provided us a set of observations for student appointments, essentially in a list form over time. Let's take a look. Tutoring Center needs to allocate tutors this week for office appointments, so it needs to forecast the number of students who seek appointments. The director has gathered the following time series data. So here's time, here's what we're observing over time. Okay, fine. What's the first question? What would naive forecasting suggest as the number of student appointments that can be expected this week? Oh, okay, now, this is going to be really easy to answer, but we should focus on that fact. Notice the way that the data has been presented: 4 weeks, 3 weeks, 2 weeks, last week. This week is essentially the next row. And the question is okay, fine, what would naive forecasting suggest? Well, the naivest of naive forecasting, what naive forecasting means is anytime you need a forecast for something, like what's going to happen, you assume that whatever just happened will happen again. Oh, okay, so in order to create a forecast to answer this part of the scenario, you say, okay, this week we'll find how many student appointments happened last week. That would be what just happened. Well, last week there was 50. Fine, that's all you have to do. 50's the answer. Oh, all right, well, part A was easy enough. What about the next part? What is this week's forecast? Okay, so we would still be down here for student appointments using a 3-week moving average. Oh, no, wait a minute. And then what's the same forecast using a 2-week moving average? We can do that. First, let's work on the 3-week moving average. To calculate that, you just say, all right, well, this is this week. This is when I would like a forecast. A 3-week moving average, I just drop back and grab the past 3 weeks of data. That's what I average. So that would basically be 80 plus 65 plus 50. That's what happened each of the past 3 weeks. Divided by 3, I get 65. Okay, that's good. 65. Then, oh, wait a minute, but we're not finished. It did ask for 2 week. That's even easier. 2-week moving average. Past 2 weeks, that would just be 65. That was 2 weeks ago, plus 50. Divided by 2, we are averaging. Oh, okay, so you'd get a slightly different forecast. You'd say, well, technically, the forecast 57.5. There's no such thing, I believe, as half a student appointment. I mean, maybe I'm wrong in the case of the Tutoring Center, but that's the result of the 2-week moving average. Great, there, that part of it's done. What they ask next? What would be this week's forecast for student appointments using simple exponential smoothing with an alpha of 0.2? Alpha equals 0.2. If the forecast for 2 weeks, ago was 90. Now wait, it would help to look at the actual formula for simple exponential smoothing. When you want a forecast, and we want a forecast for this week, right? You take the forecast for the period before. Okay, now careful, that would be last week. And you say that plus alpha, some portion of what actually happened last period, that would be last week, minus what we had forecast last period, that would be last week. Now, wait a minute. Let us look. What we're saying is our forecast for 2 weeks ago was 90. That's what the problem told us. Our forecast for 2 weeks ago. We need to be careful to keep these straight. Now, ft minus 1 refers to last week. What I really wish was I knew what was here on last week. You know, like if this was a column for forecast. I know the forecast for 2 weeks ago was 90, but I want the forecast for last week to actually officially fill in that formula right there. Oh, wait a minute. Just a little bit of scratch work. I have the means to do that, because where would the forecast for last week have come from? It would have been the forecast for the period before, which I do have. That's 90. Plus it would have been that same old alpha times what actually happened last week what actually happened 2 weeks ago, which is 65, minus what we had forecast 2 weeks ago. All right, so I do that scratch work, I get 85. You know, it's the result of this. What is this? This is the forecast for last week. Because my forecast for last week would have equaled my forecast for 2 weeks ago. I'm backing up one row in that table, plus alpha times what actually happened 2 weeks ago, minus what I had forecast would happen 2 weeks ago, which I happen to know was 90. Now, that's great. So that means my forecast for last week would have been 85, and that's perfect. That's actually the number that I need to answer the question, because that is ft minus 1. Now I know, well, it must have been 85 plus 0.2 times, now wait, what actually happened last week? Well, actually there was 50 student appointments, minus, well, what had I forecast? Apparently 85 using this particular technique. All right, now do these calculations, 85 plus 0.2 times 50 minus 85, and that's where you get 78. That would be the forecast for this week. Simple exponential smoothing is a pretty simple formula. Just remember, though, that the formula connects from one period to the next, and just make sure that you're working with the right periods each time, you know, you try to use the formula. Okay, so the forecast for this week would be 78. Now, okay, that's done. Let's look at the last part. If the director used these 4 weeks of data to create a linear regression, what does the linear regression formula suggest for this week's forecast of student appointments? Oh, great. Well, linear regression. That's what these helpful formulas in the note frame were included for. What does the regression analysis suggest in general about student appointments? At the tutoring center, I've got to find the regression equation. This is not going to be quite as fast as the first 3 parts of the scenario, but we can do this. Okay, because the key to developing a regression equation is first finding all these summary statistics, like the sum of x times y, or the average x or the average y, and then you put them into the formulas. Now, but wait. Before we even do that, we'd better back up and check that we do understand what x and y are in this particular case. Now, y is the dependent variable. It's the issue that what you're trying to forecast, what you're watching, what you're trying to anticipate. So in our case, y would be the student appointments. You know, and yeah, we have data on the student appointments. X is the independent variable. X is the issue that you think Y depends on. Now you say, well, what factor do these appointments depend on? At least what is suggested by my data. And here's the key. The only thing that you have data on, and so it's the default assumption here, is we are assuming that Y, the number of student appointments, apparently depends on time. If we're doing a linear regression and this is all the information that we have, right? Oh, okay, so X is time. Or another way to think about it, you know, when you're looking back at the original data, is X is the period, except we're going to need like a nice neat number in each case for each week for X, the period, and we don't really have that. We have descriptive language, right? 4 weeks ago, 3 weeks ago, 2 weeks ago. So this is Y in a regression study, and this is X. We kind of need to relabel the periods. This would be the easiest way to do this. So instead of speaking of 4 weeks ago, let's just, since that's as far back as we actually have this relationship, just call that the first period. Call 3 weeks ago the second period. Call 2 weeks ago the third period. And call last week, which we do have data on, the fourth period. And that implies that in the future we would keep counting up. Oh, all right. Now we have, see, just a neat column of numbers for X and a neat column of numbers for Y. Why am I so obsessed about that? Because we've got to find these summary statistics. Okay. The summary statistics, like for instance, we need the average X. Okay, so if X is time, or time periods, we need the average X, or X bar. Well, that's just 1, 2, 3, and 4 averaged together, or 2.5. We need the average Y. Well, I would retrieve that old data. Here we were averaging over here. Average Y, we average over here. What's the average of 95, 80, 65, and 50? I get 72.5. Good to know. We're going to need that. We need, for instance, in this formula, the sum of X squared. Where are we going to find that? Oh, that's pretty easy. These are the X's, right? Square them, then add them up. So basically 1 plus 4 plus 9 plus 16. I did that. I got 30. 1 plus 4 plus 9 plus 16 is 30. Okay, good. We've got that one there right then. We need the sum of X times Y. That part right in there. How are we going to find that? Oh, well, that's where we go back to our original data and we say this times this, plus this times this, plus this times this, plus this times this. So I can write that out. That would be 1 times 95, that's the top row, plus 2 times, the next observation was 80 appointments, plus 3 on the third row times the 65 appointments, plus 4 on the fourth row times 50 appointments, comes out to a rather large number. I get 650. Okay, now remember, we're just finding the parts that we need for this formula. I think that we found pretty much everything, except we also need n. Right? There's an n there, an n there. N is the number of observations. N is basically the size of the data table that you're working with. And in this particular case, there's only 4 weeks worth of data, so n equals 4. Okay, so we're going to need that number too. And we just want to note, that's actually a ridiculously small number if you were like going to do a regression analysis for real. Generally, you're going to want to like at least 30 observations in your data set, but we're just doing this as an exercise to get comfortable with the equation, so we're just going to go with it fine. N equals 4. They have 4 weeks worth of data. All right, now, why were we collecting those? Well, one way to think about it is because we wanted to fill in the formulas. You'll have to find B first, because you need that, notice, to then find A. You have to find the slope before you can find the intercept. Okay, just fill out the formula. B equals the sum of X times Y. I had done the work, that was the 650. Minus the very small 4, that's the N, times 2.5 average X times 72.5 average Y. Okay, I've got the whole numerator in that formula. Divided by the sum of X squared. I had done the work for that. That was the 30. 30 minus the 4 times the average X squared. So you'd say 2.5, except be careful. Square it first. All right, I did that work. Comes out to a negative 75 divided by 5, or in my calculator, a negative 15. That is the slope of the line. What is the intercept? The intercept, A, is the average Y. Okay, that's 72.5 minus a negative 15. So it's going to wind up being plus times the average X, which is 2.5. So I get, what is that, 72.5 plus 37.5. Oh, comes out nice and neat to 110. Now, okay, say great, you filled out the formulas, but wait a minute. What's like the answer to the question? Well, we are trying to forecast this week using linear regression. Actually, where we are is we're just about to assemble the tool to do that, because in linear regression we assume that what we're watching equals the intercept plus the slope times that factor we think it depends on. So in our case, the number of student appointments would equal or be estimated by, that's a better way to say it, 110, that's the A, plus a negative 15, or basically minus, right, the time period. That's the X. Now wait a minute. The time period, well, I'll just put X. Except that's the general tool. We wanted to use it. We wanted to use this to actually forecast this week's student appointments. Now, so what is it that we're, okay, sure. But what is it that then we're supposed to put there this week? We cannot write this week. If we go back and look, wait a minute, numerically, what is the equivalent in our little scheme of this week? This week would be period 5. We were numbering the periods starting with the oldest up to today, and then we said, you know, we'd keep going in the future, right? Which means that this week is now we're up to 5. 5 is the number. So it's basically minus 15 times 5, or 35. So we would forecast 35 students, 35 student appointments, based on our regression analysis. And well, it asks for, in this problem, it asks for the forecast. Okay, so our forecast is 35 for this week. And it does also ask, what does this analysis suggest in general about student appointments? And a lot of times you do a regression analysis to try to more interpret in general what the relationship is between the independent variable and the dependent variable, not to like forecast something in particular. Well, then fine, to do that, what is it that you would be looking at? You'd be looking at, most of the time, the slope. You say, well, okay, the slope's negative 15 in this case. Ah, yes. What's that suggest in general about student appointments at the tutoring center? They are falling through time, because time is counting up here, and every time you multiply that times B, it's subtracting out more. Oh, it appears that the number of student appointments at the tutoring center is falling each week. Falling by, say, yeah, in particular falling by, and now normally what we would say is, you know, falling by an average of 15. That's what the regression analysis is suggesting. The irony is if you look at the actual data closely, did we need to do those formulas to conclude that? It started 4 weeks ago at 95. Then 3 weeks ago, appointments were down to 80. That's a drop of 15. I mean, this is what the data happens to say. And then, what is it, 2 weeks ago, 65. It's a drop of another 15. And then last week it was 50, which was a drop of another 15 exactly. So big surprise when we employ linear regression and ask the question about next week. It suggests 35, which is a drop of another exactly 15 student appointments.